Hello everyone. In this lecture, we will analyze the concept of stress and stress-strain relationship. Let's start. Stress is defined as force per unit area. In mechanics, there are mainly two types of stresses. The first one is the normal stress. The normal stress is perpendicular to the surface, and it is represented by Greek letter sigma. The shear stress is tangential or parallel to the surface, and it is represented by Greek letter tau. We analyze the stresses acting at a point within a body by using stress elements. What is a stress element? A stress element represents the stresses at a particular point within a body. It can be a three-dimensional stress element or a two-dimensional one, as presented in these figures. We use the three-dimensional stress elements in order to analyze the general state of stress of a particular point, and the two-dimensionals are used in order to analyze the plane state of stress of a particular point. Plane stress occurs when the stresses on one surface are equal to zero. The shear stress is expressed in terms of two subscripts. The first subscript indicates the direction of the surface normal, and the second subscript indicates the direction of the shear stress. And as I indicated before, a particle or a point is represented by a cube with infinitesimal size, and as presented, we use these unit cubic elements. And we all know that a cube has 6 surfaces: top, bottom, front, back, left, and right. Therefore, on each surface, there's a normal stress sigma that is perpendicular or normal to it, and also two shear stress components, tau, that are tangential to it. And we call this the general state of stress of a particle. The normal stress can be tensile or compressive. The tensile stress tends to pull the surface out. However, the compressive stress tends to push the surface in. The compressive stresses are represented by a negative quantity or negative sign, and the tensile stresses are represented by a positive quantity or positive sign. Please recall from the statics course. When we apply the equilibrium conditions, the normal stresses along the same directions must be in pairs with equal in magnitude and opposite in directions. And similarly, again, based on the equilibrium conditions, the shear stresses within the same plane must also have the same magnitude, and two adjacent shear stresses must be either towards each other or away from each other. And in this example, this plane is the YZ plane. In other words, they should be directed in a non-continuous fashion as presented in this figure. And this property is known as the complementary property of the shear stress. Now we will analyze the normal stress under axial loading condition. Normal stress is the intensity of the force acting normal to cross-sectional area. Let's consider a two-force member under axial loading as presented in this figure. In this figure, we have a rectangular bar which is subjected to axial loading, and this force is represented by P. We know that the normal stress in that member can be obtained by finding the ratio of P over A. However, the value of sigma obtained from this equation represents the average stress over the section rather than the stress at a specific point Q of the section. Let's consider a small area delta A surrounding this point Q, and a force of delta F is exerted on delta A. When this delta A approaches zero, this area becomes a point, and the normal stress at point Q is defined as delta F over delta A. As I indicated before, the stress sigma at point Q varies across the section, and it differs from the average stress value. However, this variation is small in any section away from the points of the application of the loads. As a result, it is assumed that the normal stress distribution and axial loaded part is uniform, with the exception of the immediate vicinity of the points of application of the loads. As a result, we can conclude that an approximation using the average normal stress is generally sufficient, and we can idealize the uniform distribution of the normal stress over the cross-section. This means that we assume that the normal stress is the same everywhere on this cross-section. The integration of the normal stress over the area equals to the normal force. Shear stress is defined as the intensity of the force acting parallel to the plane of a cross-section. What this means is that instead of pulling or pushing along the length of a member like we do in axial loading, here we are looking at forces that act parallel to the cross-sectional area, trying to slide one part of the material past the other. Now, please take a look at the top diagram, figure 114. You can see two equal and opposite transverse forces labeled P and P' being applied to the member AB. These vertical forces attempt to slide the material on either side of a vertical cross-section relative to each other, producing internal shearing forces that act parallel to that section. The internal forces that resist this section are what we call shearing forces. Let's look at the second figure below now. This diagram illustrates how we can conceptually cut the member at some section C to analyze the internal shearing forces. In subfigure A, we show the cut with internal forces P and P' maintaining equilibrium. In subfigure B, we flip one half to show how the internal shear force acts in opposite direction to the applied external shear forces. This is how we determine the internal shear force at a section. Mathematically, we can define the average shear stress using the following formula. Tau average is equal to P over A, where P is the internal shear force and A is the cross-sectional area over which that the force acts. This gives us a rough estimate of how much stress is being applied per unit area due to shear. However, and this is very important, the actual distribution of shear stress is not uniform across the section. It typically varies from 0 at the edges of the member to a maximum value near the center. This is especially true in rectangular cross-sections, where the maximum shear stress can be significantly higher than the average. So, we use the average shear stress for quick estimates or in design situations where high precision is not critical. But for more detailed analysis, especially for safety-critical structures, we need to consider the full shear stress distribution. Let's now look at some practical examples of shearing stress, especially in fasteners like bolts and pins, components that are used to connect parts of machines and structures. We will start with single shear. Please look at figure 116. The bolt is passing through plates B and A. The force F is applied to plate A and equal and opposite force F' to the plate B. As these plates attempt to move in opposite directions, the bolt experiences a shearing force along one single plane right through the bolt at the interface between the two plates. Now, to understand the internal force, we draw a free body diagram as shown in figure 117. You can see in subfigure A and B how the internal shear force develops along the cross-section of the bolt. Since the shear force is acting over a single plane, the average shear stress is calculated as tau average is equal to P over A or F over A. P represents the internal shear force, F represents the external one, and A represents the cross-sectional area of the bolt. Next, let's move on to the double shear, as shown in figure 118. Here, the bolt is connecting three plates, one central plate and the two outer plates. The middle plate is trying to move in one direction while the outer plates are moving in the opposite direction. This causes the bolt to be sheared in two different planes. one between each interface of the plates. Now, let's focus on figure 119. This free body diagram shows that the total force F is shared equally between the two shear planes. So each plane carries a force of F over 2. Therefore, the average shear stress in double shear connection is tau average is equal to F over 2A. This is very important. The total shearing area is doubled, so the shear stress in each plane is effectively reduced in comparison to single shear. In summary, in single shear, there is one plane resisting to force, and tau average is equal to F over A. And in double shear, there are two planes resisting to force, and tau is equal to F over 2A. These concepts are essential in design, especially in order to ensure that bolts or pins will not fail due to excessive shear stress. We will look at more complex examples in the classroom this week, but for now, make sure that you are comfortable with drawing free body diagrams and identifying shear planes. Now let's shift our attention to another important type of stress that occurs at connections, bearing stress. Bearing stress is a compressive normal stress that develops on the contact area between two separate components, typically where a bolt, rivet, or pin presses against the surface of the plate it passes through. Take a look at figure 120. Here we see a bolt inserted through a plate. When the force F is applied to the bolt, it presses against the inner surface of the hole in the plate. At the same time, by Newton's third law, the plate pushes back on the bolt with an equal and opposite force. The contact area between the bolt and the inner wall of the hole is where the bearing stress develops. Now please look at figure 121. This figure shows the projected rectangular area that we use to calculate the bearing surface. It is based on the thickness of the plate T and the diameter of the bolt D. This gives us a simplified rectangular area of TD. A is equal to TD. So the average bearing stress is given by the following equation. Sigma B is equal to P over A, and it is equal to P over TD, where P is the applied load. So in summary, bearing stress occurs due to compressive contact forces between parts, and it is a compressive normal stress. We calculated using the projected contact area between the bolt and the plate. It is essential to check bearing stress in design in order to prevent local deformation or failure in bolted joints. We are now solving a stress analysis problem from the topic of normal stress. Let me read the problem statement. The build-up shaft consists of a pipe AB and solid rod BC. The pipe has an inner diameter of 20 mm and outer diameter of 28 mm. The rod has a diameter of 12 mm. Determine the average normal stress at points D and E and represent the stress on a volume element located at each of these points. We are given a build-up shaft consisting of a pipe AB, which is hollow, and a solid rod BC, both subject to the axial forces, and these axial forces produce normal stress. Our task is to find normal stress at two specific points, point D on the pipe and point E on the solid rod. Let's first analyze the normal stress at point E. This means that we need the internal normal force Fe. First, we draw the free body diagram and write the force equilibrium equation along the x direction. For this purpose, we will apply the method of sections by passing a section through the E point, and this will expose the internal normal force Fe. Then we solve the force equilibrium equation along the x direction, and the result yields that Fe is equal to negative 8 kN. So this means that it is a force acting along the negative x direction. As the next step, we determine the normal stress acting at point E, which is represented by sigma E, and this is equal to P over A. P represents the internal normal force acting point E, which is Fe. We have a solid circular cross-sectional area. When we substitute all of these values, the result yields that the internal normal stress acting at point E is equal to 70.7 megapascal, and it is a tensile stress because it tends to pull the section out. We can also draw the stress element and demonstrate the normal stress acting on the stress element as presented here. Then we repeat the same process for the D point in order to determine the normal stress acting at point D. For this purpose, we draw the free body diagram and write the force equilibrium equation along the x direction. We will again apply the method of sections by passing a section through the D point. This will expose the internal normal force Fd. Then we solve the force equilibrium equation along the x direction, and the result yields that the normal internal force acting at point D is equal to negative 4 kN. This indicates that this force is acting along the negative x direction. As the next step, we can determine the normal stress acting at point D. This normal stress is represented by sigma D, and it is equal to P over A. P represents the normal internal force Fd here. This time we have a hollow circular cross-sectional area. When we substitute all of these values, the result yields that the normal stress acting at point D is equal to 13.3 megapascals, and it is a compressive stress since it tends to push the section inward. We can also draw a stress element and demonstrate the stress acting on the stress element as presented here, and this completes the solution of this problem. Let's solve a classic punching shear stress and bearing stress problem. We are analyzing the average punching shear stress created by a shaft and also the bearing stress on the plate it is pressing into. We have a circular shaft with a diameter of 50 mm and it is pressing through a metal plate. The applied force is 40 kN and it is downward. The thickness of the plate is 10 mm. The plate has two shear planes across sections AC and BD. We are asked to calculate the average shear stress on the shaft at the failure planes and also the bearing stress on the plate surface. Let's start. As the first step, let's calculate the punching shear stress, which is represented by tau average. AV represents the area of the shear plane, and it is the area around the shaft which is equal to perimeter times the thickness of the plate. And AV is equal to pi times 0.05 times 0.01. Pi times 0.05 represents the perimeter and 0.01 represents the thickness of the plate. Therefore, the punching shear stress is equal to shear force, which is represented by P, divided by the area of the shear plane, which is represented by AV. When we substitute all of these values, the result is that the punching shear stress is equal to 25.5 megapascals. As the next step, let's determine the bearing stress. Bearing stress is the force divided by the projected contact area between the shaft and the plate. Please recall that bearing stress is the compressive contact stress that occurs between two surfaces. In this case, we have a shaft pushing into the metal plate, and the bearing stress is not distributed across the full cross-sectional area of the shaft. Rather, it is localized to the area of contact between the shaft and the plate. We have a cylindrical shaft pressing vertically down into a flat metal plate, and the contact area occurs along the circular ring between diameters of 120 mm and 60 mm. So this forms an annular ring on the surface of the plate. Just imagine a washer or donut shape where the shaft presses down. The projected contact area, which is also known as bearing surface or bearing area, is represented by AB, and the bearing stress is represented by sigma B. Sigma B is equal to P over AB. P represents the compressive force producing this bearing stress here, and it is equal to 40,000 newtons. and the projected contact area, which is represented by AB, is equal to pi over 4 times 0.12 squared minus 0.06 squared. So when we substitute all of these values, the result yields that the bearing stress is equal to 4.72 megapascals, and this completes the solution of this problem. We will solve more complex problems related to these two. See you soon. Bye.